So let's look at this example. We're given a sheet of cardboard, and then we take squares out of each corner, and we fold up the pieces to make a box. So the first thing to do for this problem is to draw a picture, draw a diagram. And what we're trying to do here is we're trying to maximize the volume. So what we need to do is find a volume function, and that will be our objective function. And then we can try to maximize that volume function to solve this problem. So you can see here we have our rectangular sheet of cardboard. It's 11 inches by 8 inches. And then from each corner we cut out the corner. So we're going to let the dimension of that square that we cut out from each corner, we'll let the dimensions of that square be x. That will be the side length of the square. So you can see we have all these x's. These are all the side lengths of that square that we're cutting out. Then what we do is we fold up each of those pieces, and those become, so we can make a box, and so each of those pieces we're folding up become this part of the box. So that corresponds to the height of the box. And the dimension of the height will be x, because it's coming from each of these pieces being folded up. So now we need to find all three dimensions of this box over here. We found the height, which is x. So now we need to find the length and the width. Well, to find the length of the box, it's just going to be this section right here. That section is just the total length, 11, minus an x from the left side and minus an x from the right side. So the total length will just be 11 minus x, so 11 minus 2x. And then this width right here will just be 8, because the total from here to here is 8, but we're taking away x and x, so we get 8 minus 2x. So now we have all three dimensions for our box. So this is a classic problem, and you've probably seen it before in college algebra, so hopefully it's a little bit familiar. So now that we have all the dimensions for our box, we can come up with a function that gives us the volume of the box. So you probably remember, but the volume of a rectangular prism or a rectangular box like this is just going to equal the length times the width times the height. Now I want to think of the volume as a function, so I wrote v of x to represent our volume function. So now let's just plug in what the length, the width, and the height are. And now let's just multiply all this out so we can get a polynomial written in standard form. So when we multiply all this out, we just get this. So that's our volume function, and in this case is our objective function. That's the function that we're trying to maximize. Now before we continue, let's think about what the domain for this problem should be. Now obviously, if we weren't talking about a real-world problem, the domain of this function would be all real numbers because it's a polynomial function. But let's talk about what the domain should be in the sense of our problem. So remember, x is the length of this little piece we're cutting out here. So it definitely needs to be bigger than 0. It needs to be strictly positive. But also, it can't be bigger than half of 8. So like if x was equal to 4, then we would cut out 4 inches here, 4 inches here, and we have cut out that entire side. So x needs to be less than 4. So we get our domain is from 0 to 4. I've put not including 0 and not including 4, so an open interval. You could technically include 0 and include 4, but if you did that, then your box would have no volume, so it wouldn't really make sense. So I kept it as an open interval for our domain. Okay, so now we proceed to find possible points where we can have maximum or minimum value. So let's find our critical values. So to do that, we got to take the derivative of the volume function. And so we get the derivative is equal to this. So to find the critical values, we take that derivative and set it equal to 0 and solve for x. Well, this is a quadratic function, and it doesn't look like it will be able to factor, so we can plug it into the quadratic formula. Before we do that, I can see that there is a common factor of 4 in each of these terms. So I can divide both sides by 4, which now gives me this function, or this equation. And so now let me plug that one into my quadratic formula, which simplifies to this. And now let's find our two values for x. We need to approximate the values. So we need to take the square root of 97, and we'll get a decimal number and then find the approximate x values. So we get these two values of x. Now we can eliminate this one because it's greater than 4, and we said our domain is only from 0 to 4. So now we only have one possible critical value. X equals approximately 1.525. So now we can plug this into our second derivative to see if it's a maximum or a minimum. So our second derivative function equals this, and now let me plug in the x value of 1.525, and I get negative 39.4. All I care about is that it's negative. So this tells us that we have an absolute maximum at our critical value. We know it's an absolute max and not just a relative max by the maximum principle number 2 from the last section. So we only have one critical value over the domain, and we found that that critical value was a maximum, so now we know it's an absolute maximum. So the question asks us what dimensions will yield a box of maximum volume. So what size squares should we cut out of the corner of the box, or the sheet of cardboard, to get the box of maximum volume? So we should cut out squares with dimensions, side lengths 1.525 approximately, measured in inches, and this will give us a volume of the volume function evaluated at x equals 1.525. So we can plug that into the volume function to find what the maximum volume is. So when we take that side length and plug it into our volume function, we get approximately 60 inches cubed. So that will be our maximum volume of the box. So in examples like these, you just find your objective function, whatever it is you're trying to maximize or minimize, and then you find the use the derivative to find the critical values, then use the second derivative to test if it's a maximum or a minimum.